Everyone. Welcome to the second lecture of AI Simplified series. Today we're going to talk about some of the main issues when you are dealing with when you want to train a very large model. Before we start, I want to emphasize again, like we did in our first lecture, that one of the books that is heavily being used in lesson planning here is this very amazing book. I highly recommend for those who do not have this book, go and purchase it to support the author for this great work. So in today's class, we are going to talk about the typical complications that can come from training a very large model. The issues we are dealing with is slightly different if you work with large models. Specifically, we're going to talk about vanishing and exploding gradients and how to deal with them. We're going to talk about using different types of activation functions. We're going to talk about batch normalization, gradient clipping as methods to deal with vanishing and exploding gradients. And also, we're going to start talking about something called transfer learning. This is something that's being used for large language models and also vision models a lot. This is a fascinating part nowadays. Not no one, but very few people or very few companies can afford to train a very, very, very large model from scratch. They usually use something that is already being trained before. So we're going to talk about that. We're going to talk about when you don't have like label data. How can you use publicly available data to train some model that with like limited amount of effort on labeling, you then will be able to make your model perfect. We're also going to talk about different optimization methods. And this part, I'm not going to get into too much detail of every single optimization method. Honestly, I think you usually use a few of the optimization methods and you play around with them. I don't think it's too necessary to know all the details of this one. The next one is how to deal with learning rate scheduling. And lastly, we're going to talk about regularization techniques and my most favorite part of today's course, the dropout method. Okay, so let's get started. So there are four main things that can come from training large neural networks. Large neural networks have a lot of flexibility that can almost learn they can learn any pattern that you can imagine, but they suffer from few issues. They have to be able to tackle them. One of them is vanishing or exploding gradients, not gradient, sorry for the typo here. That should be gradient. Another one is not having enough training set or label data. The next one is slow training. It takes a long time to train them. And lastly, when you have so much flexibility in your model, you can overfit. How to deal with those instances. So let's just start with vanishing or exploding gradient issue. Vanishing or exploding gradient issue comes from the fact that in back propagation, you are propagating down the error. Let's say you are using a functional form like sigmoid for your activation functions. As you can see on the tails of this distribution, the first order derivative or gradient of it is converging to 0. That means if down the road one of the weights is not updated as much, that small gradient will be propagated backwards and everything behind it will be very, very small. So that is called vanishing gradient issue. The vanishing gradient issue, we say, okay, as we will have like some layers that we have very, very small gradients, and like if you go backwards again, we have a smaller one and a smaller one and a smaller one. And as you saw in the first lecture in the backpropagation algorithm, the gradients are the absolute necessary ingredient in updating the weight. So if there is not that much gradient there, if the gradient is 0, the weights are almost never going to get updated. Another twin issue is when we have a very, very large error that is being propagated. Let's say, sorry, I said error. I should have said a very large gradient that is being propagated downward. So you have some gradients, and then that large gradient will be multiplied by another large gradient, and this large gradient is going to get also another large gradient. So the whole thing will be exploding. Once such a thing happens and your gradients are getting larger and larger and larger when you're going in your backwards in your back propagation, what will happen is your weights cannot get updated stably. It will become unstable. In one round, it increases by 20%. In next round, it decreases by 50%. The next round, it will increase by 200%. The next one, it will decrease by 500%. It becomes very, very, very unstable. So these are the two issues that in early days of deep learning considerations, it stopped the progress of neural networks. So that was why people stopped talking about neural networks. Okay, yes, theoretically, these deep neural networks can learn every single pattern that we want, but training it is another issue. Back then, people were using sigmoid function for activation function a lot, or hyperbolic tangent, or something like that back then. So how can we deal with it? There are a few ways to deal with it, but interesting enough, in 2010, two main issues for this issue was proposed. They said the authors, this is a very seminal paper, it changed the perspective about a deep neural network. They identified that, oh, maybe sigmoid activation functions are to blame, not the architecture of deep neural networks. Maybe because of these activation functions, we have been stopping progress in this field. And the next one was, they noticed that in previous lecture, we said we are I should say usually, because in transfer learning, that's a different thing. But if you want to train something from the scratch, at the very beginning, we randomly assign random weights to all the weights, and we call that initialization. They found that actually how we randomly assign weights needs to be, we should be very thoughtful about that, because poor initialization can guarantee that the variance of your output will increase over time, and that is not good. So imagine from each layer to next layer, your output gets increased. So they identified these two issues, and in subsequent papers, these authors and the rest and some other authors proposed some initialization methods. For example, they start and say, okay, in order to initialize any weight, we have to consider the number of inputs and outputs to that specific layer. So let's say the inputs in one layer are like 6 weights and the output are like 12. The way we initialize that should be completely different from the way that we are initializing something that we have like 2 weights in and 4 weights out. So these should be different. So they proposed 2 initialization methods. They said, depending on number of inputs to each layer and outputs going out of each layer, we can either use a uniform distribution and have the weights going from a negative number from a uniform distribution to a positive number, and that number is the square root of 6 divided by number of inputs and outputs. And then the next one that they suggest, okay, if we want to use normal distribution, the standard deviation of that normal distribution should be proportional to the number of inputs and outputs of that. The more inputs and outputs you have in a layer, then the standard deviation of that initialization for the weights around that should be smaller. So if you have one input and output, you have more flexibility, you have a wider distribution you can sample from. But if you have hundreds of layers in and 100 layers out, we should be extremely careful when we initialize those weights. We should keep those standard deviations or variations in check. Otherwise, we will observe exploding gradients or the other way around. The second thing they discussed was, instead of using our sigmoid functions, why don't we use more simpler forms of activation functions that have more predictable gradients, and the gradients are not exploding or converging to zero. One of the most famous activation function that has been started being used is called the rectified linear units, or ReLU, and that is 0 before 0 and a simple line from there. So for example, if x is 5, the output is 5. If x is negative 5, the output is 0. As you all know, the gradients of it, when it's 0, it's 0 because that's a horizontal line, and after that it's 1 because it has 45 degrees angle with x or y axis there. So the beauty of this one is it is a very good activation function, used a lot in practice, and it's extremely easy to compute. Exponents are costly to compute. These functions are like simplest things in the world. But they have an issue. Their issue is dying ReLU. That means some neurons effectively die, specifically when all the training set produces 0 inputs for that activation function, and it dies. So that's one of the main issues there. Despite that, it's fine. Okay, some neurons die. Okay, so what? You just use more neurons there if you want. But this is an issue. The next issue is the derivative at 0 doesn't exist, so we cannot define gradient at x equal to 0, and that's an issue because in backpropagation we need to know the gradients, and if derivative is 0 somewhere, that's a problem. So there have been thoughts to deal with dying ReLU. So two suggestions have been using leaky ReLU or parametric ReLU. In leaky ReLU, we are using 0.01 as before 0 and same 45 degrees line with respect to x. So that's x equal to y, y equal to x on the anything above 0. So that still, this is better because it resolves the issue of dying ReLU because gradients before 0 does exist, but it still have an issue. And the issue is at 0, it doesn't have gradient. You can also play with that 0.01 that is written for leaky ReLU. You make it parametric, you have alpha times a. So that will be a learning parameter. You can play with your models to learn and optimize on it. So this is another suggestion that you can use, but usually the left one is the one that is being used in practice. There are other iterations of it. For example, we have ELU, which is called exponential linear units, where after 0, x is x, but before that is alpha times exponent of x minus 1. So this way, you still will have like smaller and smaller gradients after, let's say, before -2 or -3, somewhere around there. But the beauty of it is very smooth, meaning that it has gradients in every single point. It usually converges faster than ReLU, but it's computationally expensive because for x's smaller than 0, it has exponent function in it. And as we mentioned before, this is this adds to our computational time. So it converges faster to optimal solution, or it leads to deep neural networks to get faster training in terms of number of epochs it needs to get to be used to train these models. But because of the added computation time, despite the fact rate of convergence is faster, it usually takes longer than ReLU to train these. So in practice nowadays, I don't think too many people are using ELU. But there was another one which I think was, if my memory serves me well, was introduced by Google. Another one called Swish was introduced, x times sigmoid of x. Again, this is an extremely smooth function. The gradients does exist, and these in practice have shown a lot of promise in converging extremely fast. So in the next slide, I'm going to summarize when to use which one of these activation functions. So Swish is one of the ones actually nowadays are being used. So ReLU is a good default for simple tasks. Majority people's use cases are limited to simple tasks, but Swish is a better default for more complex tasks. So if you have a lot of parameters, you want to learn extraordinary things, and your neural network is very complicated, Swish usually works better than ReLU because, as we said, it doesn't have the issue of dying neurons. And if you have more complicated tasks to do, you don't want neurons to die. If you want to have a more complex tasks, but don't want to get into like too much of the complexity of computation coming with Swish, you can use leaky ReLU. So this is the guideline to pick the activation function. So if you have a very simple task, go for it. Go for ReLU fast, and you don't care about dying neurons there. When you have a very complicated task, go with switch if computation is not an issue. So you can wait, you can spend money on GPUs and everything else, so that's fine. If you have complex tasks, but you also care about cost, probably leaky ReLU is your friend. So this is the overall guideline for using activation functions here. So far we have talked about two different ways to deal with vanishing and exploding gradients. One was choosing a different activation function, and the very first one that we discussed was some initialization methods. And the third way we can deal with vanishing and exploding gradients is using something called batch normalization. Batch normalization is a simple process. Batch normalization for every input layer, for every hidden layer, you are normalizing your inputs to center around 0, and then you scale it back when its output comes to make sure it shifts and it scales it in a way that it goes back to the original scale that it had. That way you guarantee that when your input comes in, it's not going to get affected by the scale of your input levels. Usually the input types that have higher scale have higher impact into your output. So we have always talked, so in the previous lecture we talked about normalizing our first input layer, meaning our raw data, to assure we don't deal with this scaling issue. But normalizing it will only help the very first hidden layer. It doesn't help the second, third, fourth, fifth, sixth, and so on layers. So in this method, you're assuring that in every hidden layer, before the data gets fed into each neuron, they're scaled back in a way that it is zero-centered and has small variance. And then when the output comes, you rescale it back and shift it in a way that it gains back the properties it had. I would say it's a very effective way in dealing with vanishing or exploding gradients, because some of it is coming from the scale of your input, which would be distorted inside the neural network. And another thing that it has is if you start using like batch normalization, you really don't need to standardize your input layers, raw input data anymore. You can just let the model handles it inside like hidden layers. It does it effectively. One of the issues it has, which is not a small issue, is when it comes to prediction, it adds a layer of complexity there. So batch normalization, because of this complexity in the predictions, makes things in production slower. That is why sometimes because of this added layer of complexity for predictions, sometimes it's not being used in practice. Another way to deal with vanishing or exploding gradients is to clip gradients. For example, imagine you are assuring that every time you're backpropagating, you're using backpropagation in earlier, and you go backward in any hidden layer. When you get there, when gradients are above 1, you just limit them to be 1, and when it's below -1, you limit it to -1 to make sure explosion doesn't happen. I think for those of you who have used experimentation framework, which has nothing to do with deep neural networks, you probably have observed that sometimes one of the ways to deal with outliers is to clip them. For example, let's say you are working in sales and one of the customers, on average sale is like 2,000, and one of the customers is spending $10,000 or $100,000 or $1 million there. Of course, if you're running a simple A/B test, the one that would have had that very big number would have won, because it's a very, very large number. So one way to deal with it is to cap one of the outputs. For example, you say, oh, anyone who is spending more than $3,000, we consider them as 3,000 to be able to actually run the test. Here's the same thing. We are capping our gradient to not exceed some level. Transfer learning is a very interesting field of machine learning and deep learning. The idea and premise is instead of training a very large model, let's use part of the tasks that have been already learned by other similar models and only train part of the neural network that makes sense. For example, imagine you have many layers of deep neural network for an LLM model or a vision model. So let's say there are dozens of layers here, and then like some upper level layers. So in transfer learning, what we do, depending on how much data we have available, we usually freeze training of earlier portions of it, because both in, let's say, large language models or in vision models, usually the earlier layers are specialized at doing generalized tasks. For example, in a vision model, like convolutional neural networks, probably the earlier layers are going to understand what is an edge of a shape. It can understand, like, say, circles. So this is like what it is specialized on. And then what you do is, based on the limited amount of data that you have, you only update the head of this neural network. Obviously, the more close the task that an already on hand deep neural network is, the less you're gonna need to update. So you only unfreeze like some very small part of the model, like here, and you only train that. And the less relevant the task or the more data you have, you can go a little bit deeper. But it's always the case that you are freezing training of the earlier neurons for a similar task. And as I mentioned, it's very common in LLMs, in vision models, and areas like this. We are using transfer learning. So we discussed transfer learning, and as mentioned, the more similar the task, the less top layers we need to unfreeze to train, and the other way around. And as mentioned, in LLMs and vision models, it's being used a lot. Let's also talk about pre-training on auxiliary tasks. Sometimes we don't have any data, or our labeled data are so little that we really cannot do anything with that data. Let's say you want to label, so let's say you are the first person who wants to develop, let's say, LLM models, and you actually don't have like any labeled data there. And one thing you can do is just use the corpus of data that is online. You use that, and what you do is you try some auxiliary tasks. For example, you mask some part of your data. For example, you just feed in some sentences, you mask a few of those words there, and you're trying to predict it. Or let's say you have a vision model, let's say you want to try a vision model that is able to understand noses, different types of noses on faces. Then you can just train models on the fact that I'm sure in the internet you can find pictures of people. So you just train models to identify people from, let's say, animals, and then your model is going to learn face as some of the features there. And then once you have this model which can already understand like the feature like face, then you can train it with just very limited amount of data on like noses. So that is the premise of training data on auxiliary tasks. Another way to deal with the issues that we deal with deep neural networks is usually convergence time is important because you have a very deep model and you want to make sure it doesn't overfit and so on and so forth. So what you can do, beside all of the other things we have discussed, is you use better optimization methods. That book that I told you about in the beginning of the lecture is going through many of the mathematical details of it. But what I want you to keep in mind, because this is like the standard type of optimization algorithms people use for their models, is that usually Adam optimization methods such as AdamX, NADAM, AdamW are the best one to use, and you just play around with them and you're done. So sorry that I'm going a little bit fast here, because the optimization methods are something we should care about. It's all about how your gradient, in which direction you update the weights using gradients and moments of the gradients, and so on and so forth. We are not going to spend too much on this because, as I mentioned earlier, the industry and standard is using models like AdamX and AdamW. Another interesting topic that we want to discuss is talking about learning rate scheduling. One way to train your models good is to use correct learning methods. One way is you start from a very, very small learning rate, let's say 0.00001, and on a logarithmic scale you go to, let's say, learning rate 1, and you train your model based on each one of them. As soon as you see a learning rate that starts going up, meaning that, okay, right, maybe it's better that I move back to my my notepad. So imagine this is your number of epochs, and this is your error. So let's say you use some lambda, and based on like epochs, it looks like this. You use like another lambda, it looks like this. Another lambda, it looks like this. And all of a sudden, you use another lambda that it starts going up. So the point is, you start from very small lambda, let's say 0.00001, to some lambda, let's say 1 in logarithmic scale. And each one of these training based on epochs is representative of each one of these, learning at each one of these. But as you can see here at some lambda, so let's say at lambda 0.01, you started seeing that it diverges from it. So the more epochs you learn, it start like memorizing it. So what you're gonna do is you're gonna choose a lambda that is closest to this one and is smaller than it. Let's say the previous lambda that you have used was this lambda, which was lambda 0.001. Then you can say this is the optimal lambda I am going to use. So that is the whole idea. If you want to use a very simple lambda, meaning that you're not scheduling lambda at all, that's something you can use. The other way that you can deal with learning rate, lambda or eta, depends on the literature. They use different things. They're the same. I use them interchangeably. Sorry that I used lambda before. Now I'm using lambda again. In previous lecture, I think I used eta for that, but don't confuse them. One way is to use some level of scheduling. For example, I define lambda at time t as some baseline lambda over, let's say, 1 plus t over s. C is usually 1, and s is a tuning parameter. So what it does is, let's say at t equal to 1, that means on the first epoch, I'm going to use some baseline over 1 plus 1 over s. So let's say s is 0.1, so it's lambda 0 over 1. So that means once the first round was done and you're on the next epoch, that's what you're using. The next time for t equal to 2, lambda 0 over 1 plus 2 over s would be used. And as you can see, this denominator is increasing, so that means the whole learning rate decreases. The idea is you start from larger learning rates at the beginning, and as time goes forward, you make it smaller and smaller, because the idea is you probably are farther away from the optimal solution at the very beginning. So let's say this is your objective function. I'm deeply simplifying it. So in this direction, you move very fast in the first round, then you make it smaller, then you make it smaller, get it smaller, until you get to the optimal solution. If you were to use, let's say, very large jumps at the beginning, you will go this way, then you will probably jump this way, then you will probably jump this way, and you will diverge. So one way to deal with this issue is regulating or scheduling the rate at which you're updating the learning rate that you use in your backpropagation. There are some different ways to do it. One is this one, which is what we discussed. Another one is using a simpler form in terms of like exponents, for example, lambda 0, 0.1 to the power of t over s. Again, since this is less than 1, the more t you add, so the more epochs you train it, the whole lambda t will become smaller. The idea is the same, and what we do is just scheduling the weights there. Last thing I want to discuss is two other methods that we can make sure we do not overfit. One of them is using L1 and L2 regularization. The idea is very similar to the first part of this textbook, the lectures that we have covered way before, like using L1 and L2 regularization in, let's say, linear regression lines. If you add those penalties to weights, when you're optimizing for weights, you just make sure the model doesn't unnecessarily use the weights that are not useful. So it makes a lot of weights equal to 0. L2 regularization doesn't kill any connection and shrinks it more responsibly. L1 is like everything we had before is relevant here. L1 is slightly more computationally expensive. Not all of the optimization methods can work for it. Not all of the objective functions are going to help us with that, reducing L1. L2 is usually easier to compute and optimize on. So for practical purposes, I think L2 regularization probably is more practical in most of the times, because really in deep neural networks, it's not too important which weights are having very, very small weights. But my favorite one of the methods that we can use to deal with overfitting is a method called dropout. This method is amazing, and I think it was a genius change in everything. It was a genius method that was used to avoid overfitting. The idea is very simple here. What you do is you randomly, with probability p, let's say you use a number between 0.1 to 0.5, depending on the architecture. Let's say I use 0.3. In each iteration, I am completely shutting down p%. So let's say here is like 30% of all of the neurons with all the connections that exist there from the model. And when I'm updating the weights, I only update the weights of what is left. For example, on the left picture that you see there, we shut down 2 of those neurons. That's like 40% of the inner hidden layers. And then we only update the weights that are not connected to these weights. Then in next round, we randomly pick 40% of other neurons and we shoot them down for that training purposes. And then next round, another 2, next round, another 2. As you can see, if you have a very, very deep neural network, every time you're training almost new weights that have been used before. So part of them, of course, have been used before, but I mean the combination of the weights you're updating will be different. That is going to help the model not to overfit and be able to generalize, because you didn't specialize any neuron in anything in this case, so you cannot memorize the patterns. It's a genius way to deal with it. We haven't touched on recurrent neural network or convolutional neural networks yet, but it's for those two types of architectures, usually this p, the probability of freezing any of the neurons, is between 0.2 to 0.3 for RNNs and 0.4 to 0.5 to CNNs. Again, this is an amazing, wonderful way to avoid overfitting, and it's being used in practice a lot. Thank you so much for being with us today. I wish you luck and success. See you in the next lecture.